Howdy all, and welcome back to my lecture series on introductory astronomy. Now, if you're watching these contemporaneously as I put them out on YouTube one by one, you may notice that we have skipped from lecture 12 to lecture 16. And the reason for that are both mundane and boring, so I'm not going to go into it. For those in the future, this is not an issue. So, but for those of you who are watching this contemporaneously, you may want to hold off and watch lectures 13, 14, and 15 before continuing to watch this one. I will be referring to things that we discussed in the previous lectures, but hopefully you can still follow along if you want to just go ahead and watch this. So what are we going to be talking about today? What we're going to be talking about are the endpoints of stellar evolution. Essentially, how does a star die? Astronomers tend to personalize or humanize, I guess, the evolutionary states of stars. We talk about a star being born, living through adulthood, and then ultimately dying. And so I'll probably be using that terminology. What I mean by dying is that a star is ultimately going to form an end product. It's going to form into an object that does not significantly evolve over time, or at least we don't believe so. One of them may actually evolve over time, but the observational evidence for it has yet to be discovered. And we will talk about that actually in the next lecture, lecture 17. One of the things I want to emphasize is the primary driver of what I'm going to be talking about is based on essentially one characteristic, and that is the mass of the star. There are other factors that will tweak the time frames involved, such as the metallicity, how many heavier elements that are in the star. But ultimately, the primary driver is mass. And the mass not only dictates things like the lifetime of the star, how quickly the star evolves, but also what the interior chemistry looks like. What does the interiors of these stars look like? What elements ultimately become used for nuclear fuel? And finally, how do these stars ultimately die and form these end products that I'm hinting at? So how do we know that these events, which happen during the end stages, are related to stars? Well, one indication are supernovae. These are highly energetic events. These are perhaps the most energetic event in the universe. And we identify supernovae by comparing a suddenly bright object in the sky to what the sky looked like before that thing came into being, or that we noticed that thing. We have surveyed the entire night sky a few different times. So we have plenty of base data or pre-data, a priori data, something like that. The data before the supernova. And we can compare the two. And so this I believe is supernova 1987A. Now you might be wondering about that name. The reason for it is that A, it was discovered in 1987, and 2, it was the first supernova discovered in that year, hence A. And so we look at this bright object that suddenly appeared in the night sky that someone noticed, and we quickly compare that to what the star field looked like prior to that. And we can pinpoint that that bright object could be traced to a star. And so we know that whatever is happening with that object, whatever caused that violent explosion, is tied to the existence of a star. So before we get into how stars ultimately end, let's talk about how long stars live. Now here, the life expectancy is essentially the life expectancy, as the name would imply, from birth to death. But what I'd like to emphasize is those times are almost exclusively the time frames for hydrogen burning into helium, or helium burning, or the main sequence adult stage of the star. The time frames for birth and the time frames for death are much shorter than these. And what we find is, as I said, because the mass drives things, or the mass dictates how a star evolves, we see here that there are many orders of magnitude, or a few orders of magnitude, between the life expectancy of a O star, which is, well, for example, 32 times the mass of the Sun, to small M stars, which are the smallest stars possible. We go from 2 million, or 8%, of these stars have masses around 8% of the Sun. You go from 2 million, burn bright, die young, to trillions of years old, 5.5 trillion years old. And you can see the range. The Sun, for example, has a life expectancy of about 10 billion years. So, in about 4.5 billion years, if we have not gotten off this rock, we will need to. Probably a little bit before then, maybe 4 billion years, give or take. I plan on seeing it or die trying. But I digress. As I said, take-home point here is the mass dictates the life expectancy, and it's a drastic change in life expectancy. This is not a small thing. So as we're getting in, let's start with, at the bottom as it were, with low and intermediate mass stars. Now, we, as you probably are going to guess, we divvy up stars based on their mass into 3 different categories: low, intermediate, and high mass stars. And that has to do with certain mass cutoff range. So for low mass stars are defined as stars where the mass is between 8% to 200% of the Sun's mass. We have intermediate stars, which are between 2 to 8 solar masses. I should point out also that these low mass stars, these M dwarfs, like I said, have been around for a very, very long time, and the first ones we believe were created fairly shortly from astronomical timescales after the Big Bang. So they've been around for tens of billion, or around 10 billion years or so, or even longer. And they're going to stick around for an exceedingly long time. So if the universe does come to an end in one way or another, these stars may in fact see that. These stars may in fact be around through the entirety of the age of the universe. Again, making the assumption that the universe has some sort of ending. Now, I want to remind folks of a term of which we refer as hydrostatic equilibrium. Hydrostatic equilibrium is a fancy way of saying that the two primary pressures acting on a star are equal, and those pressures are gravity trying to contract this star into essentially a point, and then radiation pressure pushing outward. Now, radiation pressure is the pressure which results from the energy produced through nuclear fusion. And so as we go through different stages, these stages are dictated whether we're in hydrostatic equilibrium or we're not. In the main sequence, we are. However, when we get to the red giant phase, we're not. Eventually, because there's only a certain amount of fuel to be had, hydrogen will eventually run out and be essentially be converted almost entirely to helium. When this happens, the core is going to shrink, because again, the radiation pressure significantly drops off as nuclear burning drops, or essentially stops. And so gravity wins, and it's going to cause the core to collapse, which brings the material around the core to collapse as well. Now, if you remember before, the key temperature for the Sun for generating nuclear fusion using hydrogen is around 10 billion Kelvin. As that material from around the core shrinks down, it heats up, and eventually it's going to get to 10 billion degrees, the magic number, and it's going to create a hydrogen fusing shell over an inert core of helium ash. As it happens, the amount of energy generated in this shell is actually larger than the amount of energy generated in the core. And so what is going to happen is that the radiation pressure from this shell is going to cause the star to expand. Now, in astronomy, as it is in physics, maybe chemistry, generally speaking, if something gets bigger, it's going to cool off. And so as the star gets larger, the surface temperature of that star is going to drop, hence why it is referred to as a red giant. In previous lectures, I talked about the color of a star in relation to its temperature. Hotter stars are bluer, cooler stars are redder. And so as this thing balloons out, the surface temperature is going to drop to 3,000-4,000 Kelvin. And it's going to become, like I said, a red giant. If we look at this as a function, or if we plot these red giants onto the HR diagram, and we see this, or we can do this, the observational evidence is looking at clusters of stars, the evolution of clusters of stars, as I've discussed in a previous lecture. And so what we find is that, as for the sun, for example, we're going to use the sun primarily as the low mass example. When the hydrogen stops, hydrogen burning in the core stops, and we go into the red giant phase, we have what is referred to as the red giant branch. We see stars moving off to the right of the main sequence and then drastically up, almost vertically, as the temperature stays constant, but the luminosity increases with larger radii. If you go back to the Stefan-Boltzmann law, which relates luminosity to both radius and temperature, in this case, the expansion of the star far outweighs any sort of the very small diminishment of the temperature. And again, we refer to this as the red giant branch. The next stage of evolution is referred to as the horizontal branch. Now, I'm not going to go really into any sort of specifics, or detail rather, but ultimately, depending on the mass of the star, it's going to go through, it's going to go on to what we refer to as the horizontal branch, and depending on, again, the mass, it will spend a certain amount of time on that branch. The sun will spend almost no time on the horizontal branch. It will go, the transition between the horizontal branch and the red giant branch and the horizontal branch, and I'm going to be saying branch a whole lot, probably more than I care to, is the initial burst of helium burning in the core. The core is continually contracting during the red giant sequence, or red giant branch. See, I was trying to avoid saying branch. Anyway, the core is contracting. It's getting, as it does so, it's getting warmer, and then ultimately it gets the magic number where helium begins to burn into carbon. And it will do that transition because of the composition, or how the core is composed. It will do so almost, or just instantly. And it will cause a tremendous amount of radiation to burst out of that and cause and begin the horizontal branch. The core will get larger, and it will push that hydrogen burning shell outward. Now, as it happens, the amount of energy that is produced in this case is insufficient to hold the star at its current radius, and so the outer layers contract and heat up, and so the surface temperature rises, the luminosity drops. The horizontal branch, like I said, is much larger, or the star is much larger when it is than it is on the main sequence, but not as large as it is on the in the red giant phase. And the lifespan of the time it spends on this branch is much shorter, as I mentioned before, much shorter than the time it spends in the main sequence. The only sort of similarity between the two is that on the horizontal branch, yet again, we have that the star is in hydrostatic equilibrium, hence why it's horizontal. It basically keeps the same radius and keeps the luminosity for as long as there is helium fuel to burn into carbon. Now, how does that work? How does that helium fusion happens? And you can see the diagram here. And what we have is that two helium atoms will slam into each other. One of the byproducts of which is a gamma ray, that is ultimately the energy that is produced in the star through this process. So energy comes out. This helium atom will, or this combination will turn into a beryllium atom, or I really should say beryllium nuclei. It's so hot that the electrons are no longer bound to anything. So you have this beryllium nuclei, and it smashes into, very, very quickly, it smashes into another helium nuclei, and the two form carbon. And another gamma ray pops out. This is also referred to, or this process is referred to the triple alpha process, because helium nuclei are referred to as alpha particles. Then we get to something. Then we get to a situation very similar to what we had before, where eventually the helium will run out, and again the core will contract, causing all the layers to contract along with it, and ultimately the material surrounding the inert carbon core is going to begin to burn helium into carbon. And so now we have two shells. We have essentially three structures. We have the carbon core, we have the helium burning shell around it, and then we have the hydrogen burning shell around that. In a sense, a star as it evolves kind of becomes an onion. And yet again, in this situation, the amount of energy being generated by these shells is larger than the energy that was being generated simply by core fusion. And so the star will expand and turn into the asymptotic giant branch. And it will essentially, if we look at the HR diagram, yet again, the temperature will decrease fairly minorly, I guess, if that's the right word, and the radius will get much larger. In fact, that the Earth will be gone ultimately. It will, if it is essentially when the size of the sun, or when the sun becomes a red giant, the Earth is going to be a scorched ball. There's no life on it. And then once it becomes an asymptotic giant branch, it's no longer going to exist ever. And in fact, Mars, depending on certain models, Mars may not in fact exist, because it's almost as large as Mars's orbit. So, as I said, mass is very important. The reason for, and because of let me collect myself for a moment. At this stage, for low and intermediate mass stars, that onion structure stops. There does not become more complicated, because ultimately you need high enough temperatures to smash things together. Technically, you have to overcome what is known as the strong force. It's called that because it's the strongest force. You need particles going fast enough, having enough kinetic energy to actually overcome that strong force and bind together. Because of the mass, and that energy is supplied through gravitational contraction. If you don't have a sufficient enough mass, that gravitational contraction is not sufficient enough to get the core hot enough to burn carbon into its next phase. And so the star really stops its journey along the HR diagram and essentially starts to die. Now, as it does so, one of the reasons why it no longer has sufficient enough mass is that it blows off its outer layers through what we refer to as stellar winds. These stellar winds contain, because of the way that the star processes chemically, there is a higher amount of heavier elements in the surface of the star than there were in previous phases of life. And this stellar wind blows off. The radiation pressure is large enough and the escape velocity is low enough on the stellar surfaces that this gas escapes. It gets blown out into space. And what we see here, and it can be blown out, stellar winds, depending on mass, can be very, very extensive and very, in a sense, violent. The amount of mass that comes off can have it move at a very high rates of speed. And when it smashes into smaller, what's the word I'm looking? Slowly. Hey, there we go. Slower particles, slower material. It will cause these what we refer to as bow shocks here. So the orange material, that is the stellar winds coming off a very bright star, and it's basically slamming into the magnetic field of this star that you see here. And so these stars lose a fairly significant amount of mass through this process. And through the process by which the star blows off its outer layers through this stellar wind process, you get the formation of what we refer to as planetary nebulae. Now, planetary nebulae has nothing to do with planets. The reason why it has that moniker is because when they were first discovered, if memory serves, by William Herschel, he noticed that they were disk-like. He didn't believe there were planets, but at the time, the only thing that looked like a disk through his telescope was in fact planets, and so hence why he referred to them as planetary nebulae. They look like planets. And so the planetary nebula have quite a bit of structure, structure to them. And again, we have different shock waves due to the processes by which the star blows off these outer layers. But the take-home point here is that the outer layers of the star expand outward and become these planetary nebula. What's left behind is what we refer to as a Proto-White Dwarf. And that is ultimately what will become the end stage of these low and intermediate mass stars. Now, as this process occurs, as this material gets ejected out into space, it's going to move across the HR diagram. Again, these are very luminous objects, but their luminosity is going to stay rather constant. And they will move very quickly across the top of the HR diagram, and they will also heat up. And the reason why they heat up is as the planetary nebula moves away, it essentially uncovers that proto-white dwarf at the very center. That proto-white dwarf is essentially the core of that star. And as I mentioned before, that core was billions of Kelvin in temperature, and so there's a lot of energy coming off that remnant. From just the remnant amount of energy that was through nuclear fusion. And so as the planetary nebula gets more diffuse, the white dwarf, or proto-white dwarf, becomes more revealed, as it were. And we get a lot of high energy radiation from it, because again, while it is not nearly as powerful as a supernova, we still have a lot of energy being produced, because again, the core is hot, and that is what illuminates the nebula. the energy hits the energy from the core, smashes, or the Proto-White Dwarf smashes into that that material which got blown off, and it causes those atoms to become excited, and those atoms produce energy upon itself and produce all manner of beautiful colors. A white dwarf will contract as it goes through its final stages. And on average, not all white dwarfs are essentially built the same. Because again, mass is a thing. But on average, a white dwarf is going to be roughly the size of the Earth. These are very, very small objects. As in terms of stellar corpses, they're actually the largest of the three. But they're roughly about the size of the Earth. And so these are very, very dense. The surface temperatures of them are around 100,000 Kelvin or so. Now, as the white dwarf evolves, ultimately what is happening is that the white dwarf has remnant energy from as I said, the nuclear burning. And it's just going to burn, or it's just going to radiate that temperature off. Kind of like a charcoal briquette. If you light a charcoal briquette, essentially if you just leave it, it's going to burn through its fuel, and then it's going to become sort of ash, and that ash is going to cool as it just radiates its intrinsic energy out into the air. And so you can think of white dwarfs as stellar charcoal briquettes. Now, why are white dwarfs stable? They don't burn nuclear fuel, so is the radiation pressure due to that leftover material, leftover energy, is that strong enough to prevent this thing from collapsing any further? And the answer to that question is no. What we have is the star is now what we refer to as degenerate. And in this case, it's electron degenerate. And the reason for this is due to the Heisenberg uncertainty principle. Simply put, it ultimately means that no two particles can occupy the same space at the same time. So no two electrons can sit on top of each other. There is enough pressure, enough gravitational pressure, which collapses these atoms and causes the atoms to become so close together that their electrons can actually meet, or in a way, the electron cloud surrounding these atoms basically touches. And then quantum mechanics tells us, but these clouds cannot overlap. Electrons cannot exist in the same space at the same time. And so what that does is it creates a outward pressure. Think of it as structural pressure in a solid. If you press down on something solid, given a certain low amount of pressure, the solid is going to stay that way. Obviously, if you apply enough pressure, it will crack and become smaller. But in this case, I like to think of this as the sort of structural pressure that is located in white dwarfs. As we will discover, though, electron degeneracy is not the end stage. It can be overridden, and I'll explain how that happens when we talk about it. Now, again, mass, and you're at the end of this, hopefully the only thing you remember is that more mass equals brighter stars and smaller white dwarfs. Again, you can think of this as a more massive white dwarf is going to have a greater amount of gravitational pressure, and so that's going to cause the white dwarf to become smaller. And so As I said before, on average, the white dwarf is about the size of the Earth, but they can be a little bit larger and they can be a little bit smaller, depending on their initial mass. There is what we refer to as a Chandrasekhar limit, named after the Indian mathematician Chandrasekhar. I'm forgetting his first name at the moment. What Chandrasekhar found out, or what he derived essentially, was that if you get to a point of 1.4 solar masses, then electron degeneracy pressure is insufficient to support that amount of gravity pushing down. And so electron degeneracy pressure will collapse. That, as the example that I was giving, if you press down on a solid hard enough, it's going to crack and into smaller pieces. Here, the core is going, or the white dwarf will collapse into something smaller. So, if you have a core that is initially larger than 1.4 solar masses, hence, such as in higher mass stars, or, as we'll discuss later, you pour enough mass onto a white dwarf such that the mass exceeds that 1.4 solar mass limit, then it cannot become then it becomes something else. It no longer is it's no longer considered a white dwarf. It is something else. Now, as I mentioned, these white dwarfs, the last stage of evolution is that they are just radiating away their inherent energy and turning into. There really isn't a name for this. Don't know quite why. Probably because we haven't actually found one. But theoretically, they exist. A white dwarf will eventually evolve and eventually cool off to become a black dwarf. It will get so cold that it has almost no luminosity whatsoever. Because thermodynamics is a thing, it's the white dwarf is going to slowly approach the temperature of its environment. Oops, wrong way. Now we get to high mass stars. High mass stars evolve similarly to low mass stars in that they become they go through an onion-like phase, and they burn hydrogen into helium and then helium into carbon, and they create shells and so forth and so on, and ultimately they will get to the point where they will have a hydrogen burning shell, a helium burning shell, a carbon burning shell, a neon burning shell, oxygen, silicon, until finally you get to iron. Now, iron is a very special material because you cannot fuse it and you cannot split it. Or at least the amount of energy required to fuse it together is smaller than the amount of energy that you get out of it. If you manage to split the iron atom, the amount of energy that you got out of it would be, again, less than the amount of energy it would take to split it. So iron is the end result. If you get to if you start burning iron, the iron won't burn into anything else, and it becomes an inert core. And you have this, like I said, this onion layer of things. So what happens to this thing once it becomes iron? Well, as it happens, the lifespan of a star at this point is located in day, or is duration of which is in days. It rapidly evolves into something else, and it goes through what we refer to as core collapse. And the amount of energy that is generated, like I said, is very, very high, because when we're talking about the density and temperature of the core at this point, we're talking over 10 billion Kelvin with a density of 10 to the 17 kilograms per cubic meter. And so that is 15 orders of magnitude more dense than water. So how does this happen? How does the this is sufficient enough that the core goes through, basically hits it just runs past electron degeneracy pressure. So how does that happen? It gets into a stage what we refer to as, it can get to a stage, if the mass is sufficiently low enough, it can get to a stage where it becomes, it can be supported through neutron degeneracy pressure. Now, how does this work? As I said before, you might be asking, well, aren't the electrons can't occupy the same space at this same time? Well, the contraction, the force or the pressure is such that it actually causes the electrons to smash down into the nuclei. And when it does so, the proton will combine with the electron and it will turn it into a neutron. And then you get a neutrino popping out of it along with a certain amount of energy. And in that process, like I said, that is highly energetic, and it creates a supernova. And we get what is known as shock waves. I talked a little bit about shock waves when I talked about stellar winds. Here are 3 different examples of shock waves. Shock waves are not homogeneous. Shock waves occur, as I mentioned before, when high velocity material slams into low velocity material. The material surrounding these stars is not, again, homogeneous. The density of material surrounding a particular star varies depending on what it is. And so, given the direction of material being blown off, and given the amount of what the density looks like, you can have a plethora of different structures that occur. Now, this particular type of supernovae that forms from core collapse is referred to as type 2 supernovae. Now, the exact reason why the supernova explosion happens, why is it that this material, when it hits that iron core, or when that core becomes neutron degenerate or less, when that material slams into that core, why it explodes violently is not a well understood phenomenon. We suspect that neutrinos play a large factor in this, in that it carries a lot of energy. It carries a lot of energy which was formed due to the electrons slamming into the protons, and that energy gets dispersed outward and carries material with it. What we get now is somewhat similar to Planetary Nebula. We get what is referred to as supernova remnants. And we have, which is, again, essentially the envelope of the star, in this case, highly enriched with heavy metals, gets blown out into space, and it also has very different, or can look very differently from one supernova remnant to another, again based on the location. And you can see the outer shock of the outer shock, which is brighter than the inner part of the supernova remnant as the material slams into the slower ISM, or interstellar medium. This is how, ultimately, these 2 processes, or really 3 processes, are why we exist. I like to say that we are all stardust. And the reason for that is true if you think of stardust as heavier elements. When the universe was created, it had hydrogen and helium and a little bit of lithium. Everything else, carbon, iron, uranium, gold, all of these elements were formed either through the process of material being blown off of a low mass star forming that white dwarf, or in the cores of high mass stars as it goes through its nuclear burning, and then ultimately gets blown off. And the supernova itself is energetic enough that you start building heavier and heavier elements like uranium and gold. That is where we believe that these occurred. So the material that makes you up is ultimately created through stars, and so we are stardust. At some point in the history of the material inside of you, that material was once part of a star. So earlier I was sort of hedging about the neutron degeneracy pressure and things, because after a supernova you can have two different corpses, as it were. You can have and the first one is a neutron star, and that occurs when that neutron degeneracy holds. The mass is insufficient to break that neutron degeneracy. Neutron degeneracy pressure can be broken just like electron degeneracy pressure can. And so, when it does so, it forms an even smaller, denser object that is roughly about 3 kilometers in size, so about the size of Chicago, in a sense, or at least downtown Chicago. Something else, so at this point, I haven't really talked about magnetic fields. There are latent magnetic fields all within the universe, and these magnetic fields get trapped and then get trapped into stars, and those magnetic fields get generated by stars. And then what we find is, as the star gets smaller, the magnetic field intensity gets larger. And so neutron stars have tremendous amounts of have tremendous magnetic fields. Just stepping back, again, the size of the neutron star is around 3 to 10 Kelvin, order of magnitude between friends. Again, about the size of a medium city, so like downtown Chicago. Now, if the density is such that if you were able to take material off of the neutron star, 1 teaspoon would weigh over 1 billion tons. And again, the gravitational field is 200 billion times stronger than the Earth, but also the magnetic field is much stronger. Now, why am I harping on the magnetic field? Because neutron stars can also look like another type of object. We talked about when things collapse, you have conservation of angular momentum. As an object is smaller, such as a molecular core from a molecular cloud getting smaller to form a star, that material spins up fairly rapidly, creates a protoplanetary disk, yada yada. Here, it begins to rotate very quickly. The magnetic, as it's collapsing down, it rotates very, very rapidly, and again, the magnetic fields become very, very strong. We want to talk about the neutron stars spinning. Some of the slower neutron stars are around 600, will rotate about 600 times every second. Sometimes what we refer to as millisecond or rapid rotating neutron stars, you're talking about thousands of times every second, thousands of times per second. Think about that for a second. Just stop and think about this. This is an object roughly the size of downtown Chicago, spinning anywhere between 600 RPM, spinning 600 times per second. Not RPM, RPS. 600 times per second, or 1,000 times per second. That boggles my mind, just that these are so rapidly rotating. And insofar that they have these magnetic fields, you also get these jets, very much like when we looked at protostars. They have jets coming off of it because of the high magnetic fields. And we start looking at black holes and supermassive black holes, those also will have jets coming off of them. Now, if the neutron star is oriented proper or oriented in a certain way, those jets will actually be or will be pointed at us. And we get what we refer to these objects as pulsars. As I like to say, all pulsars are neutron stars, but not all neutron stars are pulsars. Pulsars are dependent on geometry. If the pulsar moves, if the pulsar beam, because the magnetic field axis and the rotation axis are not aligned, this thing spins around like a lighthouse. And if it's aligned such that that beam smacks the Earth or goes over the Earth, we can see this. This was first discovered by an Irish astronomer. Her name was Jocelyn Burnell. And when she just first discovered this, she referred to this as LGMs, or little green men, because these are radio pulses that are very, very regular. Pulsars are extremely good cosmic clocks. Unless there is some reason, some gravitational reason, these stars will not change its or basically rotation speed over any kind of short astronomical time frame. So, LGMs, if I didn't already say, that referred to as little green men. Because of the fact that these were regular pulses, she was joking that maybe these were caused by, these radio pulses were actually being sent by little green men. She didn't really believe that, but at the time she didn't have any better term for it until we actually found out the physics behind why she was seeing these radar pulses. And then finally, we have black holes. So when you have cores that are more massive than 2 to 3 solar masses, what you have is that neutron degeneracy pressure cannot resist gravity. And the core becomes what is known as a singularity. We believe singularities are masses that have no radii. Now this is much more of an open question, or becoming a much larger of an open question as we get more observational evidence in cosmology. But for now, think of a black hole as something which has mass but no radius intrinsically in the black hole itself. And so if we look at this diagram, there are 3 structures to a black hole. Well, maybe 3 structures. There are definitely 2. There is a singularity and an event horizon. And then occasionally you will have an accretion disk surrounding it. What is the event horizon, you ask? Like I said, we'll get into the black hole subject in the next lecture, but ultimately the event horizon is the point of no return. If you are closer to the singularity than the event horizon, you will not escape. Assuming you actually survive the tidal forces or tidal stresses at that point. Once you get into the event horizon, nothing can escape, not even light. Here is a table which describes the end stages, or the corpses if you want to get morbid, about in relation to mass. Again, because most of the stars are low to intermediate mass, most of these end stages, or most of these remnants, are white dwarfs. And then when you have core masses all the way, and so the core mass goes from less than 1.4 all the way up to 1.4, that is a white dwarf. If the core mass is between 2.4 and roughly 2 to 3, you get a neutron star. If it's greater than that, 2 to 3, you get a black hole. And again, the table also describes what the initial mass of the star looks like. So let's refer to binary stars, or the evolution of binary stars. Now, I've described binary stars before, and simply put, these are 2 stars which are orbiting around a common center of mass, as you can see on the left. If those 2 stars are close enough, the evolution of those 2 stars are going to affect each other. Now, I also included the graphic at the bottom, because my postdoc boss, or my postdoc advisor, as it were, was the one responsible for creating this. And this is a direct image of Algol. This is what Algol looks like. The resolution isn't great, but that's what Algol looks like. Hence, the resolution is why it looks all fuzzy and blobby. But you can see the companion orbiting around Algol. Now, said, if the stars are close enough, not so much, I don't believe Algol will become this, but because of this, these interactions, you will have different planetary nebulas will have different structures. You will have phenomena known as novae, and then you might even have a supernovae coming off. And this all deals with mass transfer, the concept of mass transfer. You have a massive, well, first let me start off by talking about a Roche lobe. A Roche lobe is, you can think of it as the point where a piece of matter can gravitationally escape from that star. If it hits the Roche lobe, then any sort of perturbation outward is going to cause that gas to escape, or flow outward, or transfer outward. If you have two stars that are, and this Roche lobe is essentially traces the amount or the presence of gravity. So if you have two stars that are close enough, then the gravitation between those two is going to distort those Roche lobes into what you see here. You're going this is what we refer to as a semi-detached binary, where the two Roche lobes will actually come in contact with each other. If they're even closer, the two Roche lobes can actually form into a common sort of envelope. As these stars evolve, you have one star evolves faster than the other one. One star may be more massive than the other one, or would be more massive than the other one, and it evolves into a white dwarf. The other star will then evolve to the point that it's a asymptotic giant branch star, and the material will flow out along the Roche lobe and will dump onto the white dwarf. And there will be an accretion disk around that white dwarf, very much like protoplanetary disks around stars, and even disks around black holes, or potentially supermassive black holes. It's amazing how many things in the universe actually have disk structures. And again, very similar to those, you have every sort of ubiquitous with that. If you have a accretion disk, you're going to have strong magnetic fields. Now, the complex structure of planetary nebula, like I've said, it's due to two factors. It's one due to how the magnetic fields of the star are aligned. It also has to deal with the presence of a binary is going to affect it, and it also has something to do with the geometry of how you're looking at it. So let's look at A and C. C is the Cat's Eye Nebula, one of my favorites. I can't remember what A is. Ultimately, if you were to move around these planetary nebulae, what we would probably find is that C has the same structure as A, but we're looking down the top of it. So we're looking down into the cone of one of the cones that you see coming off of A. Now, so based on, again, the way that the magnetic fields are going to cause the material to flow, you can have something that looks like A, or potentially B, or even D. Now, the first one of these stages of evolution was actually described by Tycho Brahe, or Tycho Brahe. And he referred to it as a nova, or new star. And what you have is a star that gets brighter, but not nearly as bright as what you have with a supernova. And that brightness can last a few weeks, a few days or weeks. And in fact, certain novae, or what we refer to as cataclysmic variables, this can reoccur with a star. You can have multiple novae happening, depending on the mass of things. The difference between a novae and a white dwarf, is due to the speed of the mass transfer, or how much mass transfer there is. If the mass transfer is low enough, what you have is that the accretion, the amount of matter that is moving on or dumping onto the accretion disk and ultimately dumping onto the white dwarf, is slow enough that the white dwarf can, the hydrogen on the white dwarf can get so hot because the material is falling in. You have, again, it's going to that material is going to collapse down. It's going to be very hot, get very hot, and it's going to start burning that hydrogen into helium. And when it does so, that causes an explosion, and that is what causes that nova to occur. As we'll discuss in a few moments, if that mass transfer is high enough, then the nuclear fusion there isn't enough time for that nuclear fusion to happen before that white dwarf makes it over that 1.4 solar mass limit, and then that white dwarf will explode into a supernova. So you have the nova. You have this explosion off the white dwarf, which is why the star gets significantly brighter. This mass, which is being dumped onto the white dwarf, gets blown out into an expanding shell, and the brightness, like I said, increases. And then, in certain cases, in this case, the dwarf and the companion survive the explosion. And again, depending on the amount of time that the other stars is evolving, how much it evolves or how quickly it evolves, and how much matter is being dumped on the white dwarf, you can get these cataclysmic variables. This process can repeat itself. The material jumps onto the accretion disk and then falls onto the black hole, or falls onto the white dwarf, and then boom, you get another nova, until there is essentially no more fuel to dump onto the white dwarf to explode again. But if, again, as I said, if the mass transfer is fast enough, then the white dwarf does not have sufficient enough time to blow up, to pop off. And so what we have is the mass can exceed 1.4 solar masses and turn into what we refer to as a type 1 supernovae. And the massive explosion, both the white dwarf and its companion are blown away or destroyed. Unlike with type 2 supernovae, where you have a neutron star or a black hole remnant, in this case, ain't nothing going to survive. Nothing can survive this type of explosion. It is exceedingly powerful. Type 1a supernovae are so powerful, in fact, that we can see them on the edges of the galaxy, or the edges of the universe. They are one of the ways that we use to measure the size of the observable universe. And it is through these observations that we actually found out, or came to the conclusion, that the universe is actually accelerating in its expansion. Now, how do we classify these? We classify these based on a couple of different ways. The type 1 supernovae, A, B, and C, they have different material coming off of them, and so their spectra are going to be different than type 2 supernovas. So because of the hydrogen being ignited, that creates the type 1a supernovae, or in that process, you have a deficiency of hydrogen in the spectra. But in type 2 supernovae, you have a lot of hydrogen actually survives. So if you look at the two spectra, you can tell the difference. Also, if you are lucky enough or fortunate enough to observe the supernova as it pops off until it essentially becomes no longer observable, or no longer observable, you get what is referred to as a light curve. You have a luminosity, a raise in luminosity, and then a decrease in luminosity with two different shapes. With type 2, it rises, it peaks, and then comes down, and then plateaus at a slower drop off in luminosity. Whereas type 1As, the red line, actually have a sort of plateau after the initial explosion. So there are two ways of differentiating them. But what I want to talk about here is simply explaining what I mean by, or how, or why we can use these as distance indicators. Supernovas are standard candles. All supernovae, all type 2 supernovae, all type 1 supernovae explode exactly the same. The amount of luminosity relative to the luminosity of the sun is the same. So, if we go back to talking about light, we know that luminosity is a intrinsic property, whereas brightness is a relational property. So the brightness of an object is equal to the luminosity of the object, or proportional the intrinsic luminosity, and inversely proportional to the distance squared. So, if you know what the intrinsic luminosity is, based on modeling of supernovae, and you see and you can measure what the apparent brightness is, then you can get the distance. And with that, I bid you adieu, and I hope this lecture was helpful and coherent. I know I've lost my words a few times, but in the next lecture, we will focus more on black holes, what their structures are, and what are some of the observational pieces of evidence that suggest that black holes do exist. So, with that, I wish you all a good day, and until next time.